Let's try and understand unsupervised machine learning. Well, put simply, this is the process of taking a lot of unstructured data, running it through lots of compute, and somehow getting structured data out of it. Example, let's say that in a room there are five people talking to each other. That's a lot of unstructured data, but everybody's voice is like a thumbprint. So just by having a computer analyze it, we could split that into individual audio streams. Or say, let's say we have a lot of documents and we wish to be able to categorize them. Now, we don't know how many categories, but we want to categorize them. Lots of documents to categorize them. That would be another example of unsupervised machine learning. Or you got lots of pictures and you want to find out similarity between those pictures. This is not just recognizing faces. So let's say person X appears in these pictures. That's a very common application, but it could also be how many pictures are daytime or nighttime, how many pictures have bright lights in them, how many pictures have modern buildings versus nature. These are various categories, right? So these are various examples of unsupervised machine learning. At a very high level, you can think of unsupervised learning as something that's where data points have no labels associated with them. So you don't know what categories these will fall into. So the goal is to somehow organize the data, sort of make sense of it to get into some groups or clusters out of it. So the important point here is that unsupervised machine learning can often be a precursor to supervised machine learning. Example, let's take we have five people talking and we get individual audio streams out of them. Well, now that you have split them into those audio streams, now perhaps we can try and find out what language they are talking in. What is the sentiment? We can analyze the text, try and gain meaning or knowledge out of what they are talking about. All of that then gets into supervised machine learning. So, yes, unsupervised machine learning is often a precursor to supervised learning. Now, let's see the concept of clustering. Everybody in a crowd is their own person. Each person is a unique individual, and perhaps in an ideal world, your organization would acquire that and interact with each person in a tailored and unique way. But for now, we face a lot of limitations, and there are plenty of times when it's helpful to create groups or clusters of people that might be similar in important ways. These can include marketing segments where you might give the same ads or same offers to a group of people, or developing curricula for exceptional students like gifted and talented or artistic students, or maybe developing treatments for similar medical groups. Now, when you look at clusters in the United States, it's easy to start with each state represented separately. But it's really common practice to group these states into, say, four large sections of geographically adjacent states, like the South, the West, the Northeast, and the Midwest. And that makes a lot of sense if you're actually having to travel around from one to another. But you don't have to group them by just what's physically next to each other. For example, a soccer team has matching jerseys and they coordinate their movement because they are a team. They could serve as the basis of maybe a behavioral cluster as opposed to a geographic one. And you can use a lot of different measures for assessing similarity, not just physical location. You can look at things like a k-dimensional space. So you locate each data point, each observation in a multi-dimensional space with k dimensions for k variables. So if you have 5 dimensions, that is k is 5. If you have 500, then you have 500 dimensions. What you need to do then is you need to find a way to measure the distance between each point, and you are going to do one point every other point, and you are looking for clumps and gaps. You can measure distance in a lot of ways. You can use Euclidean distance, that's the standard straight line between a multidimensional space. You can use things like Manhattan distance and Jacquard distance, cosine distance, etc. There are a lot of ways in which you can measure the distance or similarity between points in your dataset. Let me give you a real life example though of cluster analysis. So, for instance, one of my favorite studies is based on what's called the Big Five. The Big Five is a group of five very common personality factors that showed up in a lot of different places under a lot of different situations. The actual factors are extroversion versus introversion, agreeableness, consciousness, neuroticism, which means your emotions change, and as opposed to stability, and then openness, specifically openness to new experiences. One study I know, I actually tried to group the states in the US using these big five personality factors. They got information from social media posts and then evaluated each state and created a profile. And from that, they found that the states in the US went into three broad groups. The big group, there in orange, down the middle. They are called the friendly and conventional. The yellow, off to the west coast, and actually a little bit off on the east coast, they are called relaxed and creative. And then in green, which is mostly the northeast but also Texas, is temperamental and uninhibited. And these are different ways of thinking about the kinds of things that people think about and the way they behave. Now, you could use psychological characteristics, or maybe you could group states by, for instance, how they search for things online, which might be more relevant if you're doing e commerce. So, I went to Google Correlate and I chose a dozen of search terms that I thought might roughly correspond to the big five personality factors. And what that data tells you is the relative popularity of each search term on a state by state basis. I then did an analysis doing what's called a hierarchical cluster, where all the states start together and then it splits them apart one step at a time. And you can see, for instance, that my state of Utah is kind of unusual by itself over here. But you can see the degree of connection between each of the states. But I could say, give me two groups, and then it groups them this way. You can see that we have just five states over here listed on the right. Or we could say, give us three groups, in which case all it does is separates Utah from other five. But you can go down to a level that seems to work well, something that makes sense and that works with your organization's needs. Now, I want you to know that when you're doing a cluster analysis, you can do a hierarchical clustering, like which I just did, and that's a very common approach. But there are a lot of alternatives. You can do something called as k-means or a group centroid model. You can use density models or distribution models or linkage clustering model. Mostly, I want you to be aware that these alternatives exist and they can be useful in different situations for putting your data together. Remember, with any analysis, something like clustering exists to help you decide how you want to do the things. So use your own experience and your common sense as you interpret and implement the results of your analysis. Let's look at a common machine learning algorithm called clustering, and specifically k-means clustering. This algorithm is often confused with k-nearest neighbors, but the only thing that they have in common is that they both start with the letter k. Remember that k-nearest neighbors is a supervised machine learning algorithm. You are classifying data based on what you already know. On the other hand, k-means clustering is an unsupervised machine learning algorithm. You will use it to create clusters based on what your machine sees in the data. Think of it this way. Imagine we are back at the animal shelter in Chicago. The shelter had a large social room where all the dogs get together and play. The dogs acted like people. They had their group of friends and they chatted and hung out with each other. Each time they had a social hour, they would self organize themselves into different groups of friends. Now imagine that the shelter was closing and all the dogs were going to be distributed into three different shelters across the city. The organizers of the animal shelters got together and decided to make it easier on the dogs. They would cluster them based on the group of friends. So the shelter decided to create three clusters. That means the k in k means equal 3 because you want to divide the groups into three clusters. Now imagine that the machine learning algorithm got started. To start, the machine put a red, yellow, and blue color on these three random dogs. Each color represented a potential cluster based on their social group. These will be your three centroid dogs. Now each of the centroid dogs would look at the mean distance between itself and all of the surrounding dogs. Then the machine would put the same color collar on the dogs that were closest to these centroid dogs. As you can imagine, since these centroid dogs were randomly selected, there is a pretty good chance that you won't really have any good clusters. Maybe all the three centroid dogs were in the same social group. If that happens, then most of the dogs would have a very large distance between these three centroids. So the machine will try over and over again until it picks the best centroid dog. It might even do this one cluster at a time. At the end of each iteration, the machine learning algorithm checks the variance between each dog and the centroid. Once you have a good centroid dog, then it's pretty straightforward to put unknown dogs into each cluster. If you put a new dog into the social area, then you can tell which social group it ends up in just measuring the distance from the centroid dog. Also keep in mind that the dogs themselves did not cluster into three groups. There might have been 5 or 6 different social groups, but there are only 3 shelters, so the machine learning algorithm has to do its best to create clusters that best represent the dog's social grouping. You should also watch to make sure that you use k-means clustering if the dogs are predisposed to these social groups. If the dogs are jumping from group to group, then it will be really difficult to form real clusters. This is sometimes called a high overlap of data. Another challenge with k-means is that it can be very sensitive to outliers. So if you have a dog that's really not interested in hanging out with any other dogs, it will still be clustered into one of these three groups. So in a sense, the dog will be forced to find friends. Organizing dogs into three clusters for three different shelters is probably not a problem that you'll run into every day. But k-means clustering is actually one of the most popular machine learning algorithms. One of the more interesting applications is when retailers use clustering to decide who gets promotions. They might create three clusters that they call loyal customers, somewhat loyal customers, and lowest price shoppers. Then they'll create strategies to try and elevate somewhat loyal customers to loyal customers, or they could just invite their loyal customers to participate in one of their programs. Many organizations are looking for better ways to cluster their customers. If you can get all your loyal customers into one cluster, then that can really improve your business. Now let's do an example of how to apply k-means in practice. I will show you a visualization tool that I found online and that I think does a really great job of helping you see what k-means clustering does. And that should give you a good intuition for how it works. So I'd like to give a special shout out to Naftali Harris who wrote this visualization and very kindly agreed to let us use it. I'll share a link to this website so you can go and play around with it on your own. So it starts by asking how to pick the initial centroids of my clusters. I'll start out with randomly right now. What kind of data would I like to use? There are a number of different things here and I encourage you to play around with them. A Gaussian mixture has been really similar to one of the examples we've done so far. So Gaussian mixture data looks like this. These are all the points that we have to classify. The first question for you is how many centroids do you think is the correct number of centroids on this data? And I hope you said 3. It's pretty obvious that there should be 3 centroids here. So let's add 1, 2 and 3. So they are all starting out right next to each other. But we'll see how, as the algorithm progresses, they end up in the right place. One of the things that's immediately apparent once I start assigning my centroids is that these colored regions is how all the points are going to be associated with one of the clusters. So you can see the blue is probably already in reasonably good shape. I would say that we got a bit lucky in where the initial centroid was placed. It looks like it's pretty close to the center of the blob of data. With the red and green, it looks like they are sitting kind of right on top of each other in the same cluster. So let's watch as K-means starts to sort out this situation and get all the clusters properly allocated. So I will hit go. The first thing that it does is it tells me explicitly which cluster each of these points will fall into. So you see we have a few blue that fall into the wrong cluster over here, and then of course the red and the green. So this is the association step, and all the points are being associated with the nearest centroid. And then the next thing that I'll do is I'm going to update the centroid. So now this is going to move the centroids to the mean of all the associated points. So in particular, I expect this green point to be pulled over to the right by the fact that we have so many points over here. So let's update. Now this is starting to look much better. If we were to leave everything as is, you can see how the clustering was before. So now all these points that used to be green are now about to become red. And likewise, with a few blue points over here, you can see even just in one step from this bad initial condition, we've already started to capture the structure in the data pretty well. So I'm going to reassign the points, iterate through this again to reassign each point to the nearest centroid. And now things are starting to look very consistent, very consistent. They are probably just one or two more iterations before we have the centroids right at the middle of the clusters. So I update and reassign points. No points have changed. So this is the final clustering that would be assigned by k-means clustering. So in 3 or 4 steps using this algorithm, I assigned every point to a cluster and it worked in a really beautiful way for this example. Now that I have explained the theory of k-means clustering to you, I am going to show you how to use the Scikit implementation to deploy it in your own studies. So I start over here at Google and I find that there is a whole page on clustering in Scikit-learn. The first thing that I notice is when I get to the page is that there are many types of clustering besides just k-means clustering. So all of these different columns here are the different types of clustering. We won't go into all of these. Instead, I want to use this page to navigate to the k-means documentation so that you can get a little bit of better idea of how this is handled in Scikit-learn. So here's a list of all the different clustering methods that I have. And here, the first item on the list is k-means and some summary information about the algorithm. And so one of the parameters that you have to define for k-means is the number of clusters. Remember, we had to say at the outset how many clusters we want to look for. And this is one of the things that can be most challenging about using k-means, and that is deciding how many clusters you want to try. Then it gives us some information about the scalability, which basically tells us how the algorithm performs as you start to have lots and lots of data or lots of clusters. A use case which gives us a little bit of information that this is good for general purpose when you have clusters that have even number of points in them and so on. And last, that the way that k-means clustering works is based on the distances between the points. So very consistent with what we have seen so far. Let's dig in a little bit deeper. Now we are at the k-means documentation page, and there are 3 parameters in particular that I want to call your attention to. First and most important is n underscore clusters. The default value for n clusters is 8, But of course, we know that the number of clusters in the algorithm is something that you need to set on your own, based on what you think makes sense. This might even be a parameter that you can play around with. So you should always be thinking about whether you actually want to use this default value or if you want to change it to something else. I can guarantee you that mostly you're going to want to change it to something else. The second parameter I want to call your attention to is max iteration equal to 300. Remember that we are using k-means clustering and we have an iteration that we go through as we are finding the clusters where we assign each point to a centroid and then we move the centroid, then we assign the points again, we move the centroids again, and each one of those assign and move steps is an iteration of the algorithm. And so max iter actually says how many iterations of the algorithm do you want to go it through. It will usually be a very reasonable value. In fact, most of the time, I would guess that it's going to terminate before it gets to the maximum number. But if you want to have a finer level of control over the algorithm and how many times it goes over through that iteration process, this is the parameter that you want. And then the last parameter that I'll mention, another one that's very important, is the number of different initializations that you give it. Remember, we had said that k-means clustering has this challenge that depending on exactly what the initial conditions are, you can sometimes end up with different clusterings. And so then you want to repeat the algorithm several times so that any one of those clusterings might be wrong. But in general, the ensemble of all clusterings will give you something that makes sense. That's what this parameter controls. It's basically how many times does it initialize the algorithm, how many times it comes up with clusters. You can see that by default it goes through at 10 times. If you think for some reason that your clustering might be particularly prone to bad initializations or challenging initializations, then this is the parameter that you might want to change. Maybe bump the number of initializations up to a higher number. But again, just to reiterate, of all those parameters, number of clusters is definitely the one that's most important and the one that you should be playing around with and thinking really hard about the most. Now this wraps up what we are going to talk about in terms of the k-means algorithm. Let's recap k-means clustering. So k-means clustering is an unsupervised machine learning algorithm that can be used to predict subgroups within a dataset. With k-means clustering, you can usually have an idea of how many subgroups are appropriate. Use cases for k-means clustering include market price and cost modeling, insurance claim fraud detection, hedge fund classification, and customer segmentation. The k-means clustering algorithm is a simple, unsupervised algorithm that's used for quickly predicting groupings within an unlabeled dataset. Predictions are made based on the number of centroids present, that's the k value, and the nearest mean values given with a Euclidean distance measurement between observations. Things you want to keep in mind with k-means clustering is that you need to scale your variables, and it's a good idea to look at a scatter plot or a data table to estimate the number of centroids to use for the k parameter value. So, this might not make a lot of sense to you now, but I'm going to show you how to do this in the coding demonstration. So here we are in our Jupyter notebook, and we load the NumPy, Pandas, Matplotlib and sklearn libraries. Then in cell 2, we import the k-means from sklearn.cluster. Then we also need to import the Access3D, and we are going to use a built-in dataset from sklearn. So we'll import that too. In cell 6, we are first going to load in our data. We are going to be working with the iris dataset in this example. So we'll say iris is equal to, and then we'll just call the load iris method from datasets. And our X data is going to be our iris data. But we need it to be scaled. So we'll call the scale function and then we'll pass in the iris.data. And then our Y is going to be a data frame. So we need to call our data frame constructor and we'll pass in our iris target. This is going to be our species type that we are actually predicting for. In terms of variable names, we also need to create a variable for that. So I'm going to say variable names are equal to, and then we'll just access the feature names from within our default dataset. And then let's just print out the first 10 records here real quick. So 0 through 10. So now this is what our X data looks like. Now coming to cell 7, we are going to cluster this data. So the first thing we'll do is instantiate a clustering object. We'll call it clustering. Now in this example, we'll say that there is 3 clusters. So we are going to say n clusters is equal to 3. That's our k value. And then we want to set a seed for our random number generator. So we are going to say random state is equal to 5. Then we need to fit our model to our data. So we are going to say clustering.fit and pass in our data. So what's printed out here in the output of cell 7 is the default parameters for our clustering model. So now let's go ahead and plot the model outputs in cell 8. So let's create a data frame called iris_df. So our variables will actually be sepal length, sepal width, petal length and petal width. And our y variable, we need to set a column name for that. So we'll say y.columns is equal to targets. Now coming to cell 9, let's create a color theme for our scatter chart. So we'll call it color theme and we'll set it equal to numpy array, and that's got 3 colors: dark gray, light salmon and powder blue. And for this data visualization, we'll create a subplot that has 1 row and 2 columns. The third parameter will be exactly the position I want this next plot to come in at. So we want that to come in at the first position, so I'll pass in a 1 here. Now we'll plot our petal length along the x-axis and our petal width along the y-axis. And then our x dataset is going to be iris_df.petal length, and our y variable is going to be iris_df.petal_width. Our color is going to be represented by C here, where C is equal to color_theme. And we want to color according to this target. So we are then just going to say iris.target. And in terms of size, let's set S is equal to 50. Now for the title of this chart, let's call it ground truth classifications. Now let's create our second plot for our subplot. And this time we are going to create a plot that shows the predicted values for y. So now let's set up our plot like the previous one. In the output of cell 9, it looks like the model did a great job of actually predicting the clusters themselves, but the labeling is off, meaning that just labels of the clusters have received the wrong numbers. That's actually not a big deal. It happens quite often, so you just need to do a relabeling. So in cell 13, we'll choose the numpy_choose function to do that. Let's create a variable called relabel, and then we'll say np.choose. And then what we want to do is we want to take our clustering labels and we need to relabel them. So I'm going to create a list of new labels here. This is basically just going to assign the label numbers to the clustering labels that have been predicted by our model. So now this is going to relabel our clusters. And we just need to adjust the code for the plots from the previous cell just a little bit. So instead of using the original clustering labels to do the color assignments, we are actually going to use this relabel object that we created. So cool. Now that we have relabeled our clusters, you can see that our k-means algorithm did a close job of actually identifying which data points fall in which cluster in the output of cell 13. So on the left, that's the ground truth classification. We actually do know the cluster groupings. These are actually iris species, and we know that from our data exactly how they should have been grouped. And so visually we can tell that our algorithm did a pretty good job. But we also want to evaluate our clustering results using a classification report. So to do that, in cell 14, let's call a print function.
and we'll pass in the classification report, and then we pass in the y and our relabel object, and here are the results. So our classification report is giving an average precision of 83 and an average recall of 83. So before looking at the actual numbers, I want to explain to you that the precision is a measure of model's relevancy and the recall is a measure of the model's completeness. What you are going to go for in machine learning is a high precision and a high recall model. That indicates that you have high accurate model results. So looking at the results of our model evaluation, you can see that under the precision for all points predicted to have a zero label, 100% of the retrieved instances were relevant. That's indicated by 1.0. And then for all points that were predicted to have a 1 label, 74% of the retrieved instances were relevant. Looking over at the recall metric, for all points that were labeled 2, 72% of the results were returned as truly relevant. Of the entire dataset, 83% of the results that were returned were truly relevant. Just remember that we are going to go for a high precision and high recall. That wraps up the things for k-means method. Next, I'll be showing you the hierarchical clustering.
Hierarchical clustering is an unsupervised machine learning method that you can use to predict subgroupings based on differences between data points and their nearest neighbors. Each data point is linked to its neighbor that is most nearby according to the distance metric that you choose. I know this may sound a bit confusing, but think of this analogy. Imagine you are a geneticist and you want to identify the functional groups of genes by analyzing gene expression profiles or profiles that identify all of the genes active within the cell. You decide to apply hierarchical clustering to identify these groups based on the distance between data points and their nearest neighbors in the gene expression profile. Data points that are most similar are clustered together into the same genetic functional group. Hierarchical clustering predicts subgroups within data by finding the distance between each data point and its nearest neighbor, and also linking up the most nearby neighbors. You can find the number of subgroups that are appropriate for a hierarchical clustering model by looking at a dendrogram. A dendrogram is a tree graph that's useful for visually displaying taxonomies, lineages, and relatedness. Let me show you how to use a dendrogram. Imagine that you want a maximum distance between a point and its nearest neighbor. You want that maximum distance to be 150. You could plot out your dendrogram and then you would set a line where y is equal to 150. Then along that line, you look at each point where your dendrogram intersects the y equals 150 line. So you have 1, 2, 3, 4, 5. If you wanted to have a maximum distance of 150 between each point and its nearest neighbor, you would have 5 cluster centers. You could also set the maximum distance between the points to be 500, and in that case, you would have 2 cluster centers. That's what we are going to do in our coding demonstration. Popular use cases for hierarchical clustering include hospital resource management, business process management, customer segmentation analysis, and social network analysis. Before moving into the coding demo, I want to tell you how important model parameters are. Before moving into the coding demo, I want to tell you about important model parameters. You are going to have a set of parameters for distance metrics and linkage parameters. Distance metrics can either be set as Euclidean, Manhattan, or cosine. And the linkage parameters are WORD, complete, and average. Basically, with hierarchical clustering, you can try every combination of parameter settings that are possible, and the model that returns the most accurate results is the one you go with.
So here we are in the Jupyter notebook, and in cell 14 we will import the standard libraries we use like NumPy, Pandas, Matplotlib and Seaborn, and as well as scikit-learn. I do want to show you some extra libraries that we are going to use for hierarchical clustering. So in cell 15, we want to go ahead and from sklearn.cluster, you want to import agglomerative clustering, and then you also want to import Skippy. We are going to use Skippy for this demonstration. Now from Skippy, you need to access the cluster hierarchy module, and we need to import dendrogram and linkage, and as well as fcluster and some other modules. Now that we have all our libraries set up, in cell 16, we'll set some parameters for plotting with matplotlib and seaborn. So that's good to go. And then in cell 22, we load the empty cars dataset, and we have provided a column names as a list. So what we are going to do here is we are going to create a dataset called X, and X is actually going to be our cars dataset, but we only want to select the MPG variable, the displacement variable, the HP variable, and the weight variable. And then we are going to say dot values because we only want the values from our car dataset. And our target is going to be the AM variable. This variable describes whether the car has an automatic or manual transmission. So we are going to set y here equal to cars, and then we are going to call the ilog method, and we are going to select the column at position 9. I only want the values, so I am going to say dot values. And so now we have our data. So let's use Skippy to generate a dendrogram real quick. I'll call in the linkage function on dataset X in cell 18. This function carries out hierarchical clustering on our data. I'll pass in the word argument so that the function deploys word linkage methods. We'll call the output of this Z. So Z is the clustering result that has been generated from Skippy's hierarchical clustering algorithm. Now I want to generate a dendrogram real quick. So we are going to call the dendrogram function in cell 19, and we are going to pass in our clustering results Z. We want to pass a parameter that says truncate mode equal to last p, and p is equal to 12 with leaf rotation equal to 45, and leaf font size is equal to 15, and then we'll set show contracted equal to true. Let's just create a title for our plot, and we'll call it truncated hierarchical clustering diagram, and then our x-axis will be cluster size, and for our y-axis we'll call it distance. So now let's set a line for our y-axis so that we can count how many clusters to use in our model. Having the line really helps to make sure that we get an accurate count of the predicted number of clusters. So we are going to say plt.axh line for horizontal line, and for the first horizontal line y is equal to 500, and then we'll also set another one at y is equal to 150, and then we'll say plt.show to show our dendrogram, and there we have it. This is our dendrogram. Now coming to the output of cell 19, let's use what we know about our dataset in order to pick an approximate number of subgroups. We know that we are working with a cars dataset and that there is the AM variable. The AM variable assumes one of two positions. It's either a 0 or a 1 for automatic or manual transmission. Based on that and the results I'm seeing here in the dendrogram, I'm going to pick 2 as the number of clusters to use in our model. You can see from our dendrogram, if we are using a 2 cluster model, that's really saying that we have a distance between data points and its nearest neighbors, and that distance should be set at maximum of 400. This is because that's where there are actually 2 clusters in the model. Based on what I know about the data, 2 seems like a reasonable number of clusters. So we are going to say we want to have a max distance between data points of 500, with 500 set as our maximum distance between nearest neighbors. And this is both based on our dendrogram and what we know about our data. So now it's time to generate hierarchical clusters in cell 23. So we are going to set k is equal to 2, and then what we are going to do is call our agglomerative clustering function, and we are going to say n clusters is equal to k. That's the number of clusters we want to be used in the model. and we are going to say affinity is equal to Euclidean and linkage is equal to Ward. Now we are going to call this whole thing H clustering. This is going to be our clustering object. So now we'll fit this model to our data by calling .fit method on H clustering, and we'll pass in our data X. And let's really quickly generate an accuracy score. So we are going to call accuracy score function sm.accuracyscore, and we'll pass in our Y and our H clustering labels as hclustering.labels underscore. So now we are going to deploy each and every type of different combination of parameters that are possible with this dataset in order to see which one produces the best results. So in cell 24, for the second iteration, I'll change this Ward to average and run that. And then again in cell 26, because I'm going to change Euclidean here to Manhattan, and since we know that Ward can only work with Euclidean distances, we need to change our linkage here to average. Now what we do is, we look at the accuracy scores of our models to see which one performed the best. It looks like 0.78125, and that's here with our Euclidean affinity. Both average and Ward linkages are performing the same, and that's the highest score we generated using hierarchical clustering. Each of these two parameter settings looks like they do a pretty good job for the dataset, and that's how you perform hierarchical clustering. So next, let's look at the dbScan algorithm. dbScan is an unsupervised machine learning method that clusters core samples from dense areas of a dataset and denotes non-core samples from sparse areas of that dataset. An example of where you could use dbScan is, imagine that you are working on a computer vision project for the advancement of self-driving cars. You've got some line data that's supposed to represent lanes, but you need to be able to predict lanes from lines. You can use the dbScan to predict lanes based on the density of the lines. Dense areas would be clustered into core samples, which will be considered lanes, and non-dense areas or sparse areas will be considered as non-core samples or non-drivable areas. This way, the car knows where to go. You can use dbScan to identify collective outliers. Just make sure that the number of outliers you choose is less than 5% of the total number of observations in your dataset. You do that by adjusting your model parameters accordingly. There are two important dbScan model parameters. Those are EPS and min samples. EPS is the maximum distance between two samples for them to be clustered in the same neighborhood. You want to start at an EPS value of 0.1. Then min samples are the minimum number of samples in a neighborhood for a data point to qualify as a core point. You want to start with a very low sample size. Looking now at our Jupyter notebook, we'll include Pandas, Matplotlib, Seaborn, and scikit-learn libraries in cell 11. I've also given the parameter for Matplotlib's data visualization in cell 12. So let's go ahead and create a dataset. We'll call it data. Data is equal to df.ilog, and then we are going to select the first four columns. So we are going to say colon, and then we want to select 0 through 4, and of course we just want to bring in the values, so we are going to say dot values. So now for the target feature, we are going to call that target, and then we are going to select that from our data frame, but we are going to select that in the very last column, the species column, which is at index 4. Just to give you an idea of what the data frame looks like, let's just print out some values over here. And in cell 14, you can see that we have sepal length, sepal width, petal length, and petal width. So these are our four columns for our data, and then species is going to be our target, and that's what we are predicting for. The next thing is that we need to instantiate a dbScan object in cell 15, and we'll call it model. So we'll say model is equal to dbScan, and then we need to pass in the parameters for EPS and min samples. You want an EPS that is equal to 0.8, and that will just tell Python that we want a maximum distance of 0.8 between two samples in order for them to be considered as in the same neighborhood. As far as min samples, we want to set that equal to 19. What that tells Python is that each point must have a minimum of 19 samples to be considered as a core point. And then we call the .fit method on this data. Next, I'll go ahead and print out our model. So you can see here, these are the default model parameters. We've got the EPS, which we set manually, and also the min samples, which we set. Now that we have our model, let's go ahead and use it to identify some outliers in cell 16. To do that, we are going to create an outliers data frame called outliers_df, and then we are going to call our data frame constructor 3d.dataframe and we'll pass in the data. Now remember that we don't want to use any more than 5% of the data points to be labeled as outliers, so we need to check that proportion. To do that, we'll simply print out the model labels. So you could just call the print function, and then within it you will pass the counter function and pass within that the model labels. Also, let's print up the records that we had labeled as outliers. Then we can begin to look at our results. So to print those out, we are going to say print, and we are going to print out the outliers data frame. But we only want to print the points that have model labels equal to -1. And I am going to create a quick visualization of our clustering results in cell 17. So to create the visualization, we first need to generate a figure called fig, and we'll add in an axis, and then we'll pass in a list that says what we want in our axis to be. So it will be 0.1, 0.1, 1, and lastly 1. And we'll set all colors equal to our model labels. So now it's time to create a scatter plot. So we are going to call the scatter function, that's ax.scatter, and let's just print out the column at index position 2. So we'll say data, and then we'll select the variable at column position 2, and then also we'll include the column at index position 1, and we want our colors to be equal to the model label. So in cell 17 output, we see a scatter plot of our findings. So here is our scatter plot, and then these are the printouts of the outliers we identified with our model. So these were the records that were identified with a -1 value. Now what I want to point out here is that our counter returned how many records have been assigned to a label of 1, how many have been assigned to a label of 0, and how many have been assigned to a label of -1. The records with the label of -1s are considered outliers. That's only 4%, so 4% is pretty perfect. Just remember that you always want to have less than 5% of your dataset marked as outliers. It's important to know that which records those are. So I created a data frame that returned the row index values of each of those outlier records. And then our data visualization. DBScan has identified collective outliers. That's why they are all appearing together in an anomalous portion. The red and the pink areas, DBScan has considered those to be the core samples. Those are generated from the dense areas of the dataset. But see what's circled over here in red. Those are what we call the collective outliers. So now we come to feature scaling. Feature scaling is an important step in pre-processing your features for some types of machine learning algorithms. We'll talk a little bit more about this in the next lecture also, but let's develop some intuition for it. We need to apply feature scaling to our data, mainly to prevent the features with larger magnitudes from dominating the prediction model. Let's go back to the dinosaurs age and imagine that we need to count the number of living species in an island from top down with a drone. When we look down from a higher distance, bigger animals like dinosaurs will be quite visible. However, it will be rather difficult to count the smaller animals like ants. In order to have a fair glass to see all the variables from the same lens, we'll apply some methods. This way, the prediction models will perform better. Two methods we'll discuss here are called normalization and standardization. These methods are commonly applied to variables x, and scaling the target values y is commonly not required. Let us start with the first method, normalization.
It's also referred to as min-max scaling. So let me give you some intuition for what it accomplishes and what can go wrong when you don't do feature scaling. So let's suppose I have a buddy Chris, and Chris wants to know what t-shirt size should he wear. For some reason, he doesn't know his t-shirt size, but he does know two good friends Cameron and Sarah and their t-shirt sizes. Chris can get the data from Cameron and Sarah about how tall they are and how much they weigh. And based on this information, Chris can tell what t-shirt size he should be wearing based on whether he is closer in size to Cameron or Sarah. So here are some numbers to make this more concrete. Chris is tall and very skinny. He weighs 140 pounds and he is 6.1 feet tall. Cameron is also fairly tall but not quite so skinny. He clocks in at 175 pounds and 5.9 feet. And Sarah's pretty petite. She is 115 pounds and 5.2 feet tall. Cameron, of course, wears a large t-shirt size, whereas Sarah wears a size small. And we'll assume for the sake of argument that there is no such thing as a medium in this example. So my first question to you is, should Chris wear a large like Cameron or a small like Sarah, based on his height and his weight? And I would say that Chris would be much happier in a large size. He does weigh less than Cameron does, but he is quite tall, a bit taller than Cameron, and certainly much taller than Sarah. So I think putting him in a small would be pretty uncomfortable for Chris. Now let's suppose you are a computer who's trying to answer this question and you don't have any particular knowledge about what height and what weights are. But you can compute numbers pretty easily, and the metric that you will use is height plus the weight. Whoever Chris is closer to in height plus weight metric, that's the size he'll wear. So the first question is, what is the height plus weight for Chris? Height should be measured in feet and weight is measured in pounds. And for Chris, the height plus weight is 140 pounds plus 6.1 feet. That's 146.1. Next, let's do the same thing for Cameron. What's his height plus weight? The height plus weight for Cameron is going to be 175 plus 5.9, or that will be 180.9. And lastly, let's do that for Sarah. What's the height plus weight for Sarah? Sarah will be 115 plus 5.2 or 120.2. And now here's the most important question of all. Who is Chris closer to in height plus weight? Remember, this will be basically the answer of what size shirt should Chris wear if you are a computer doing this calculation. Should he be wearing a large shirt like Cameron or a small shirt like Sarah? And the answer very counterintuitively is that by this metric of height plus weight, he should be wearing a small size like Sarah. Now remember, using our intuition, we said that he should be wearing a large size like Cameron. So what went wrong here? So the way that I got this result, that Chris should be wearing a small size t-shirt as Sarah rather than Cameron, is that I compared these numbers that I computed for each of these people. And I said, is Chris closer to Cameron's number or to Sarah's number? And as it turns out, he's about 26 away from Sarah and he's about 35 away from Cameron. So closer to Sarah. Now what went wrong here is that the metric of height plus weight has two very imbalanced features in it. That's height and weight. So here's what I mean by that. The height is going to be a number that generally goes between, let's say, the number of 5 and 7. The weight, on the other hand, takes much larger values, between 115 and 175 pounds in this example. So what ends up happening here is that when you compute the sum of these two, is that weight completely dominates over the answers. And the height ends up being effectively a rounding error. Whereas what you probably want is something where the two features are equally weighed in. And this is what feature scaling does. It's a method for rescaling features like these ones, so that they always span comparable ranges, usually between 0 and 1. So then the numbers that you get from height will be between 0 and 1 and they'll still contain the same information but just expressed in different units. And the weight, it will also be expressed between 0 and 1. And again, we'll still have the information there that Cameron raged the most and Sarah the least, but it will be expressed over this much smaller range. Then when you add them together, weight won't completely be dominating the equation anymore. And when that happens, you should get a much more sensible result for Chris's t-shirt size. Because even though he's a little bit closer to Sarah in weight, he's a lot closer to Cameron in height. And so he'll probably end up getting grouped with Cameron. One of the nice things about feature scaling is that it's fairly straightforward. There's a formula and you just have to apply it to your data. Here's the formula. X prime is the new feature that you're making. And you use the information about the old features to figure out what value it should take. Xmin and Xmax are the minimum and maximum values that are taken by the old feature before it was rescaled. And X is the old value of the individual feature that you are rescaling. So just to make this a little bit more concrete, let me give you an example. Suppose the old weights, the feature that we want to rescale, are 115, 40 and 175 pounds. If this is the old feature, what is Xmin? In this example, Xmin is going to be 115 because it's the minimum value that's taken on by the old weights. If this is your input data, what is Xmax? Xmax is going to be 175 pounds because it's the greatest value of the feature that we see it take on before we do any rescaling. And now I want to use this information to rescale a feature. So the feature I want to rescale is to find X prime of 140. So what is the 140 pound feature after you've done the rescaling? Remember, the Xmin we just found is 115 and Xmax is 175. So you figure out what to plug in into this formula to find X prime 140, the rescaled value to the 140 pound person's weight. The answer that you get when you use this formula is 0.417. So 0.417 is the new value of the feature that belongs to the 140 pound person. So the way we did this is we take our Xmin and Xmax and we plug them into the formula, and we plug in 140 as well in the position for this sort of old feature of X, and then we can compute X prime. And one of the features of this formula for rescaling features is that you will transform features always between 0 and 1. Now this has some benefits and some disadvantages. One of the benefit is that you will have a very reliable number as to what you can expect in the output. One of the disadvantages is that if you have outliers in the input features, they can kind of mess up your rescaling because Xmin and Xmax might take extreme values. In the other method of standardization, we first subtract the mean value from the number and divide by the standard deviation. In this case, we do not have a specific range we are staying in, unlike the case with normalization. This method is less affected by outliers.
So now let's move on to PCA.
Principal component analysis is an unsupervised machine learning algorithm that discovers relationships between variables and reduces variables down to a set of uncorrelated synthetic representations called principal components. For an example, imagine that you work at a major grocery store chain and you've got some data that was generated by customers making purchases with their rewards card. The dataset describes customers and the products they purchase. You need to identify what key factors, perhaps age or income, that most affect the customer's purchasing behavior. You can use PCA to decompose your customer purchasing data into one vector that describes the factors that influence the customer's purchasing behavior and another vector that describes the probabilities that products will be purchased based on those key influencing factors. Principal components are synthetic representations of a dataset. Principal components contain all of the dataset's important information but do not include the noise, information redundancies, and outliers that were present in the original dataset. Popular use cases for PCA are fraud detection, spam detection, speech recognition, and image recognition.
So here we are in the Jupyter notebook and we import the standard NumPy, Pandas, Seaborn as well as scikit-learn in Cell 4. And I just want to show you how to import the decomposition module as well for the principal component analysis algorithm. So in Cell 5, first of all, we need to import the decomposition module from sklearn, and then from the decomposition module, we import the PCA. So now our libraries are loaded, and coming to Cell 7, we are going to work with the Irish dataset. So this is the dataset we are going to be practicing our principal component analysis on. So you have your data source here. Let's just start by printing out a sample of it. So we'll say X and we'll print out the first 10 records. So this is your dataset and you can get an idea of what it looks like from the inside. The next thing we need to do is instantiate a PCA object in cell 8, and then we are going to say decomposition.pca, and then we'll apply the dimension reduction on X. So we'll call this output iris underscore PCA, and we will set that equal to pca.fit underscore transform, and we'll pass an X. Lastly, let's print the explain variance ratio attribute. This is useful for seeing how much variance is explained by the components that were found. So to print it out, we'll just say pca.explained underscore variance underscore ratio. Now just let's quickly generate a sum in cell 9. So we are going to take our explained variance ratio and we want to call the sum method off of it. So as you can see, the explained variance of all the components is adding to 1. Let's take a look at actually what all this means. First, you need to understand what explained variance ratio is. This ratio tells us how much information is compressed into the first few components. You can use explained ratio variance to calculate a cumulative variance. Then, with this cumulative variance, you can figure out how many components to keep. You just need to make sure that you have at least 70% of the dataset's original information. So now turning back to the results from our analysis, when we sum up the variance that's explained by all of the components, it adds up to 1. This will be our cumulative variance. This means that 100% of the dataset's information is captured in the 4 components that were returned. That's great, but we don't want 100% of the information back. Remember, some of that information is tied up with the noise, information redundance, or it represents outliers. So our goal is to remove all that junk and keep only the fundamental or principal components that matter. Look at the explained variance ratio in output of cell 8. We can see that the first component explained about 92.4% of the dataset's variance. That means it holds about 92.4% of the data's information in one principal component. Pretty cool, right? And by taking the first 2 components, we only lose about 2.3% of the dataset's information. That's the junk we want to get rid of anyway. So let's do that. We will take only the first 2 components and feel satisfied knowing that they contain 97.7% of the Irish dataset's original information. So now coming to cell 10, let's make a data frame so we can look at our principal components. We'll call it comps and we'll just say comps is equal to pt.dataframe, and then we are going to pass in our principal components. So that's pca.components underscore. And then we want to pass in some variable names. So we are going to say columns is equal to variable underscore names, and then we'll just print these out. So in cell 11, we also want to take a look at the heat map. So correlation of heat map is here to see how the datasets variable correlate with the principal components. So to do that, we are going to use Seaborn's heat map function, which is sb.heatmap, and then we'll pass in our comps. And then let's just set a color scheme for this. So we'll say CMap is equal to blues. And how about let's add a little annotation. To do that, we'll say annotation is equal to true. So the explained variance that we looked at earlier told us that the first 2 principal components contained 97.7% of the dataset's total information. Based on that information, we decided to keep only two components. The results from our correlation heat map show that one principal component is strongly positively correlated with petal length and moderately positively correlated with sepal length and petal width. Component 1 is slightly negatively correlated with sepal width, and principal component number 2 is strongly negatively correlated with sepal length and sepal width, and slightly negative correlated with petal length and petal width. You may be wondering how you can use these components once you have isolated them. Well, you can use them as input variables for machine learning algorithms. So in the case of Irish dataset, you could use these two components we've generated as inputs for a classifier in order to predict species labels for new incoming data points. If you're still with me at this point, great job. I think PCA is one of the trickiest topics in machine learning. So if you're still sort of struggling to wrap your head around it, don't worry, that's normal. Let me take this opportunity to just briefly review PCA at a very high level and give you a kind of working definition that you can use in the future. So PCA is a systemized way to transform input features into their principal components. Then those principal components are available to you to use instead of your original input features. So you use them as new features in your regression or classification task. The principal components are defined as the directions in the data that maximize the variance, which has the effect of minimizing the information loss when you perform a projection or a compression down onto those principal components. You can also rank order the principal components. The more variance you have in the data along the principal component, the higher that principal component is ranked. So the one that has most variance will be the first principal component. Second will be the second principal component, and so on. Another thing that we should point out here is that principal components are all perpendicular to each other. So the second principal component is mathematically guaranteed to not overlap with the first principal component, and the third will not overlap with the first through second, and so on. So you can treat them as independent features in a sense. And last, there is a maximum number of principal components that you can find. It's equal to the number of input features that you had in the original dataset. Usually, you will use only the first few handful of principal components, but you could go all the way out and use the maximum number. In that case though, you are not really gaining anything. You are just representing your features in a different way. So the PCA won't give you the wrong answer, but it doesn't give you any advantage over using the original input features if you are using all principal components together in a regression or classification task. So now that you have a good intuition for what PCA is and how to use it, the last example I am going to give you, starting very soon, is one of the coolest examples of where PCA can be actually used in the wild. But before we get into that, let me just pause and talk you through when you want to use PCA. When is it an appropriate approach? The first one is if you want to access latent features that you think might be showing up in the patterns of your data. Maybe the entire point of what you are trying to do is figure out if there is a latent feature. In other words, you just want to know the size of the first principal component. The second one, of course, is dimensionality reduction. There is a number of things that PCA can do to help you on this front. The first is that it can help you visualize high dimensional data. So of course, when you're drawing a scatter plot, you only have two dimensions that are available to you, but many times you have more than two features. So there is a kind of struggle to how to represent 3 or 4 or many numbers about a data point if you have only two dimensions in which to draw it. And so what you can do is you can project it down to the first two principal components and just plot that and just draw the scatter plot. And then things like k-means clustering might be a lot easier for you to visualize. You are still capturing most of the information in the data, but now you can draw it with those two dimensions. Another thing that PCA can help you with is that if you suspect that there is noise in your data, and in almost all data there will be noise,
The hope is that the first or the second, your strongest principal components, are capturing the actual patterns in the data, and the smaller principal components are just representing noise variations about those patterns. So by throwing away the less important principal components, you will be getting rid of that noise. The last one is using PCA as a pre-processing before you use another algorithm. So a regression or a classification task. As you know, if you have a very high dimensionality and say a classification algorithm, the algorithm can be very high variance and it can end up fitting to those noise in the data. It can also end up running really slow. There are a lot of things that can happen, and then you have very high input dimensionality with some of those algorithms. But of course, the algorithm might work really well for the problem at hand. So one thing that PCA can do is reduce the dimensionality of your input features, and this helps the classification algorithm work better. So that's a wrap on PCA.